Welcome to part 4 of the machine learning tutorial. We're going to talk about model validation now. Model validation goes into more depth as to how we can evaluate how well our model is actually doing. In particular, we haven't talked about what data we want to use for training our model and what data we want to use for calculating something like accuracy. And it turns out we want to use different data to do that. Generally speaking, you want to at least have a two-way split. You want to have a training set that you train your model on, so that you use to determine your parameters using, for example, gradient descent, and you want to have a test set. And the basic idea is you train your model on the training set, then make predictions on the test set, and then you calculate something like an accuracy. We will get more later into the reason for doing this, but essentially the idea is that you don't want your model to just memorize information in the training set, but you want it to be able to generalize to new, previously unseen data. There's an extension of the scheme called cross-validation. So in addition to the training and the test data, you have a cross-validation set. And this comes into play if you have a so-called hyperparameter that you want to select. So for example, if you think back to gradient descent, there was a learning rate that we could choose, this one here, epsilon. Now, sometimes if you choose a different learning rate, you might get a better model performance. For example, what you can do is you can take a learning rate of 0.1, a learning rate of 0.01, and one of 0.001. Each time you train on the training set, you make predictions in the validation set and get something like an accuracy. And then you compare the three results from the validation set. The one epsilon that gives you the lowest error or the highest accuracy on the validation set is the one you will choose. And then you will make a final prediction on the test set to give you an unbiased estimate, a most accurate estimate of the true error. So this scheme is generally used if you have hyperparameters that you want to determine. There's a more involved way of doing this, but it leads to a more accurate assessment of your true error, and it's called k-fold cross-validation. In k-fold cross-validation, you first split off your test data. You don't touch this until the very end. Your non-test data, you will split into k equal parts, for example, 10 parts. You will then train your model on k minus 1 of these parts, so for example, these 9 blocks here of your non-test data, and then evaluate your error on the whole dot set, or whatever metric you're using. Now you have an error. You will then do the same thing, but this time the data that you're holding out will be a different block. You will train on these 9 parts of the non-test data, get an error on the whole dot set. And you keep cycling through this, you will get 10 errors. You then average all these errors. This will give you cross-validation error for each choice of hyperparameter that you have. So, for example, with the 3 epsilons, you'll get 3 averaged errors, and then you choose the parameter with the lowest error rate. So the difference is, the difference to the previous slightly simpler scheme is, you essentially do the cross-validation, you calculate this 10 times and then average. And in the final step, you then look at the test error once you have determined your best epsilon, for example. And your tested error is then what you will choose to report.